Alright, I hope you guys are doing well, and in this video we're going to be going over the entirety of Exam 1 for Organic Chemistry 2, and in this video I'll be covering version A. Version B should be the same, just a little out of order. So without further ado, let's get started with question number 1. In this molecule shown below, each nitrogen has a lone pair. I'm going to immediately go ahead and draw those out. For each labeled nitrogen atom, we have A and B. The lone pair of the electron is in blank, and we have a bunch of different orbitals. So when approaching an orbital question like this, first of all, I would like to draw out the orbitals. So for example, the nitrogen, you have an orbital coming out here, an orbital going here, and an orbital going here. On this nitrogen B, we have an orbital here, 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 and here. That just kind of really helps me visualize of where to go off of. So in this case, we're asking the lone pair of electrons is in which pair of orbitals. So if you guys aren't familiar with this molecule, is actually imidazole. Imidazole, I think I spelled that correctly. And it is a very common molecule, and I would definitely get to know that nice and well. So in this case, we want to know what orbital these electrons are in. So let's start with the nitrogen labeled A. So in this case, we want to take a look at whether or not this molecule is aromatic. In fact, we do know that this molecule is aromatic, right? So we have this lone pair here, we have a lone pair here, and a lone pair here, and that satisfies Huckel's number. So in this case, the lone pair on the nitrogen for A is going to be in an sp2 orbital because it's currently not participating in the aromaticity that the molecule already has. So we can go ahead and eliminate A and B because it says that it's in a p orbital when we know that it's in an sp2 orbital. So let's go on with the B nitrogen. So we can see here that in this case, in order for this molecule to be aromatic, the electrons, the lone pair, need to be participating within the aromaticity and to Huckel's number. So in this case, it will be in the p orbital, because for all these aromatic compounds, all the electrons are going to be orbiting in the p orbital, hence making answer choice C the correct answer. Cool, so now let's go on to question number 2. Cumene is a common name for a benzene ring that has a blank. So this is basically kind of testing, do you know what this common molecule is? If you have it memorized, cool. If you don't, then you are screwed. So cumene is going to look a little something like this. It literally says it has a benzene ring, and in this case, it has this group coming off of it. So once we know that, we can kind of go off of these answer choices. We can immediately eliminate methyl. That does not make any sense. We could immediately eliminate a pair of methyls because there's only one group sticking out of that benzene. This is not going to be a tert-butyl group because it has only 2 carbons coming off of this carbon right here. So now we're left with an isopropyl and a propyl group. In this case, it's going to be an isopropyl group because it attaches at the midpoint between these 3 carbons, making it an isopropyl. Cool. So now let's go into question number 3. Which of the labeled positions would experience appreciable EAS, SEAR in the molecule undergoes nitration? So basically, this is aromatic electrophilic substitution. So basically, this is asking, hey, do you know your activators and deactivators, if that makes any sense? So in this case, I would note that for the D hydrogen, I can automatically go ahead and rule out that is probably not going to occur there because in nature, we don't want, or I guess the molecule is not going to favor anything that is too sterically strained. You see here that the bromine in this big group here is kind of blocking that space. So the next step here is to look at this amide kind of group here, or amine group here, niamide, and this is going to be an activator, which is going to direct ortho-para. So ortho is going to be right here, and para is going to be right here. This is meta-directing, which is not going to go and direct there, so our answer choice is going to be C. Question 4. NH3 plus is a blank. This is kind of going back to do you know it or not, and this one is a strong deactivator. Okay, question number 5 and 6. Use the following molecules below to answer these questions. So let's go ahead and use the dollar method that we learned. So let's look at molecule A first. We have this group of carbons here. This is going to be +1. And we have these halogens here. all the halogens are going to be minus 1 for a total of a net of minus 1. Let's look at B here. We have a carboxylic acid and a chlorine here. Carboxylic acid is going to be a moderate deactivator, minus 5. Chlorine is going to be minus 1 for a total of minus 6. Right here we have a nitro group here. This is going to be very, very strongly deactivating, minus 10. And we have a methyl group here. We have plus 1 for a total of minus 9. Let's look at D here. We have this alcohol group and this kind of sulfonyl group here. We automatically know that this alcohol group, we should know that is plus 10, and this sulfonyl group here is going to be a minus 10 for a net of 0. So automatically looking here, out of all the 4 that we've done so far, D is actually going to be the fastest, even though it is 0. Let's look at E. We have this amine group here. This is going to be strongly activating. We're going to give this a plus 10, and this iodine here, it is a halogen. It's going to be a minus 1 for a total of plus 9. So now we know which one's the fastest, and now we know which one is the slowest. So let's look at question 5. Which will react fastest? We know now it's E. Which of the molecules will react slowest? It's going to be C. In general rule of thumb, if you guys are kind of confused of whether something is activating or deactivating, if, for example, let's look at B, we have all this resonance up here. Resonance can occur here, it can occur here. This is kind of withdrawing the electrons out and kind of pulling the resonance there, if that makes sense, which makes it deactivating. Same thing with this one. We have a lot of resonance here, kind of pulling the electrons out there, as opposed to, let's say, E, we just have lone pairs here, and this amine group cannot it can't really suck out the electrons, so it can actually push in the electrons into the ring, which makes that faster. So if you guys are kind of stuck, you can kind of look at the resonance. I guess this whole course is all about resonance, right? So that is definitely a very helpful rule of thumb if you guys get stuck. So question 7 asks, which of the following is anti-aromatic? If we remember what anti-aromatic is, it's basically is the molecule aromatic but has an even number of a pair of electrons. So let's look at A. We can automatically rule this out. Why? Because this right here, sp3 carbon, that is no good. That won't make it aromatic or anti-aromatic at all. Let's look at B. We have 1, 2, and in this case, these electrons are drawn like this, but if a molecule or an atom can push its electrons in here to participate in aromaticity, then it can. So in this case, this is going to be aromatic. It's not going to be an option. For C here, we have 1, 2, 3. This is not going to be any good. For E here, we have 1, 2, 3 pairs. That's not going to be any good. If we look at D, we have a ring structure, and it has 1 pair, two pairs for an even number of pairs of electrons. So that's going to be your anti-aromatic compound. Let's look at question number 8. Which of the following is the correct frost circle? So if you guys remember how to draw frost circles, for example, we have this 7-membered ring. We would always draw the tip at the very, very bottom. So we can automatically rule out answer choice E because the tip is at the top here. That doesn't make any sense. And the next step is to kind of fill in the electrons of where they would go first. So let's count the number of electrons. 2, 4, 6, 8. We have 8 electrons. So we can automatically rule out A. That has 6 electrons. So let's look at answer choice B. We have we want to fill in the electrons from the lowest to the highest. Nature is a couch potato. I'm pretty sure Dr. Berg has said that a bunch of times. It wants to be as lazy as possible, fill in the most convenient spots before going on to the more energetically unfavorable. So in this case, B looks like a promising answer. Let's look at C. C also kind of follows a similar principle, but if you remember from Gen Chem, we know that electrons must fill one at a time in the orbitals before maxing it out. So in this case, this does not make sense. And let's look at answer choice D. I didn't even notice this, but this is an octagon. That doesn't even make sense at all. So we could have immediately ruled out A, D, and E, and then we would have been stuck between B and C, and in this case, B is the correct answer. So let's look at question 9. The common semi-systematic name for this compound is, so this is another one of those like, do you know it or you don't? In this case, the answer is acetophenone. For answer choice 10, or sorry, for question 10. In electrophilic aromatic substitution, the Sear reaction of benzene, bromine, and FeBr3, benzene acts as a blank of the reaction. So if you guys have a quick refresher, this is the reaction that it's talking about, FeBr3, and this is going to add, it's basically just going to brominate a benzene. So in this case, we could automatically rule out activator and deactivator. That doesn't make really that much sense. Acid doesn't really make sense in this context as well, so now we're stuck with nucleophile and electrophile. And if you remember from Organic Chemistry 1, nucleophiles are going to be very electron rich. So benzene obviously has a bunch of electrons, so this is going to be our nucleophile. Now, next part, we have nomenclature. Let's start with question 11. First, we always want to find the parent chain, and in this case, ignore this benzene. That, although you might want to start here, you're going to quickly find yourself running into a wall because it's going to be a struggle. In this case, the alcohol is going to take the priority of what is going to be the parent, so we're going to name that with the lowest number possible. We're going to go 1, 2, 3, 4, 5. And if we name this out, it's going to come out to be 4-phenyl. Remember, benzenes as a side chain is going to be called phenyl. It's a 5-membered chain, so it's going to be pentan. The alcohol is on carbon 2, 2-ol. 4-phenyl, pentan, 2-ol. And a cool trick to make sure that these namings make sense is if you remove this number here, can it still make sense when you say it out loud? 4-phenyl pentanol, which does make sense. It sounds correct, so you can just stick the 2 back in there if you guys want to double check. Let's look at question number 12. This is one of your main parent chains that you guys should be familiar with. Do not forget them, right? This is going to be your benzoic acid. So we're going to start numbering here, and then obviously we're going to go to the left. It wouldn't make sense to go all the way around. So this is going to be 2-methyl, and this is benzoic space acid. Don't forget the space. Let's look at question 13. A lot of people tend to get tripped up. They might think that this is a parent chain, but that is just not the case. It's very tricky. NH2, where we're going to see a little bit later on, is going to be the one that takes priority. So even up here it says the order of substitution naming, and NO2 is not anywhere to be found. So let's get started here by numbering. The numbering scheme is going to be 1, 2, 3 going this way, or 1, 2, 3 going that way. And in this case, since we have a tie within the numbering scheme, we're going to go with what alphabetically makes the most sense. So chlorine is going to come before nitro. So the numbering is going to go 1, 2, 3 this way. So now we're going to name based on alphabetical order: 2 bromo, 1 chloro, and this is going to be 3 nitrobenzene. Cool. Now let's look at question 14. In this case, NH2, this is something you should know. This is going to be aniline. And we can name this as carbon 1 and go from there. We want the lowest number order, so we're going to go this way: 2, 3, 4, 5, and 6. So now let's start the naming. We're going to go alphabetically. 2 bromo. And we have 2 chlorines, so we need to add a di in there as well. 3, 6 di, chloro, and then aniline. So now, question 15, we have an OH and an NH2, and you might be kind of at a crossroads here, but thankfully, we're given a little cheat sheet of which comes first. And in this case, the alcohol is going to take priority, and this common name is going to be phenol. And then the NH2 is going to drop down and just become amine. Amino phenol. Cool. Now let's look at question number 16. Starting here, we have this phenol group here, and this group here. This is our benzaldehyde, and benzaldehyde is going to take priority. So we're going to start naming here for the lowest numbers. We're going to go right to left, 1, 2, 3. So this is going to go OH as a side chain is hydroxy, 3 hydroxy, and this is benzaldehyde. aldehyde without a space. Benzoic acid has a space, benzaldehyde does not. Cool. Let's go to part 3, question 17. We have mechanisms in the synthesis. For the following molecules shown below, draw the other reasonable resonance contributors. The box is provided, circle the resonance contributor that is the major contributor to the resonance hybrid. So we always want to read the question as carefully as possible. So in this case, we have this molecule here. We can draw the resonance structure. Remember how electrons can door hinge over. This is a very, very important concept. So we're going to draw these electrons as door hinging here because there is a lack of electrons over here, giving us this structure. The electrons, the positive charge is going to move right there. And this can door hinge over one more time, giving us a structure that looks like this. It's asked us to circle the one that's most contributing. And in this case, the answer is going to be the middle one, because the positive charge is going to be on the most substituted carbon. Let's look at question B. We're going to same idea. We're going to draw the resonance structure. In this case, we're going to door hinge this guy down, and if this goes down, we don't want this Texas carbon here. These are going to door hinge back up. We're going to have a structure that looks like this. A lot of times people forget that these double bonds can actually go up onto the carbon next door, and we're going to have a structure that looks like this. If you ever get stuck, for example, doing resonance, and you're not sure where to go, let's say this one, the structure that we're given has a positive charge and a negative charge. You can look at the new resonance structure, and if it has a positive charge or negative charge, typically you're probably going to be on the right track. This isn't a hard and fast rule, so do be careful, because sometimes the positives and negatives can cancel out, and there will be no charges existing, like in the next example that I'm going to do right now. So this is going to collapse down. These are going to swing back up, and we're going to have a structure that looks like this. So now it's going to ask us which one is going to be the most stable, and in this case, it's going to be this one right here. And this is because there are no opposing charges. And given all the other things considered, we have the same number of bonds. It's just the fact that this one has no opposing charges, which makes it the most stable and hence the biggest contributor to the overall resonance hybrid. Let's go to the next page here. The series of reactions, and it's very gracious to tell us that Friedel-Crafts cannot occur with a meta-directing present. So automatically, I'm just going to scout this out. We have a meta-director here, deactivator, Friedel-Crafts, no reaction. This is not going to occur. This acid is our problem child. It's basically going to make it so this is not possible. So let's look at the first question. We have a nitration reaction. And we have this methyl group here, which is ortho-para directing. So we have ortho, which is going to be here, and para, which is going to be on the other side. You can draw it either like this, or you can draw it on this side as well, the NO2. It doesn't really matter. It's the same molecule. And now we got this phenol with fuming SO3 and H2SO4. And in this case, it's a strong activator, so you might think that it goes ortho-para, but like organic chemistry and chemistry in general, there are exceptions to everything. And in this case, the exception is that this is only going to add in the para position, which is very annoying, but it is something that is very important to know. So we already said that this next reaction is going to be no reaction, and now we have this NBS and peroxide reaction with this benzene type structure. Let's go ahead and draw this out. This is basically going to add a bromine at the first carbon coming off of the benzene. Whoa, what happened? Okay, the next step we have this NaOTBU, and then heat, and this is an elimination reaction, if you guys remember from Organic Chemistry 1. And it's going to eliminate this, and it's going to form a double bond like that. So now let's look at the next set of reactions. We have a activator here that's going to direct ortho-para. So we have a Friedel-Crafts kind of reaction here, and since this is an activator, it directs ortho-para, Friedel-Crafts can occur. So we're going to have this being kind of added here. We have this a double bond at O, and something that looks like this. And now we have a reduction reaction. This is another way of saying H2PD on C. A lot of students in office hours get that confused, but don't forget you have that reaction in your repertoire that is going to reduce that, add the hydrogens there. And last but not least, we have the bromination with light and heat, and that's going to add right here. I'm going to give a final product that looks like this. And the last reaction, we have chlorination here with a bunch of orthoparas, directors everywhere. Like we previously said, this right here, there's a lot of steric strain. Very unlikely that that is going to occur there. Let's look at all these carbons. This one is gonna direct orthopara, so it's probably gonna direct here. This carbon right here, orthopara, like we said, it cannot go here. Para, right there, is it could go there. And this group here, we have orthopara, very likely to go there. So in this case, the chlorine is very likely to be added right here. Now let's look at the next reaction. Draw the complete mechanism of this C reaction of the nitration of benzene. So it's very helpful to draw an overall reaction. We have benzene, we have nitration, HNO3, H2, SO4. This is terrible handwriting, and we're going to get something like this. So if you kind of know where we're going to, it's very easy to deduce the intermediate steps. So it's going to say draw out the complete mechanism, so we need to show the formation of an electrophile, we need to show all products being created, show all non-zero formal charges, use any convenient base when possible. So it is very important to read the instructions very, very, very thoroughly. So we have the nitration of benzene. So in this case, we have this nitro group here. This goes back all the way to Gen Chem. Can you draw Lewis structures? This is going to be your HNO3. It looks a little something like this. And the H2SO4 is going to be our little acid catalyst. It's going to look like this. Boom, boom. And this is basically what it's going to do is take this hydrogen from the H2SO4. This is going to collapse back down onto the oxygen. And this is going to form this ion here. We have HSO4. We have an ion here in solution, and then more importantly, we have our ion here. This is going to have a positive charge here and a negative charge here. So in this case, with a little bit of resonance, these electrons are going to collapse back down to here. This is going to kick off water, and this is going to give us something like this. So this is going to be what we're going to be working with. This is going to be your electrophile. Cool. So now we have this group here as serving as your electrophile, and benzene, like we previously mentioned, is going to be your nucleophile. This is going to basically swing up here, attack this nitrogen. These are going to collapse back down. Draw the equilibrium arrows. We're going to have a little something like this. The nitrogen, oxygen. This is going to have a negative charge right there. This is going to have a positive charge. It's going to look something like this with a positive charge here. And it does say draw out all the resonance structures, so we're going to go ahead and do this. These electrons are going to swing up here, cause the positive charge to move down there. Right? Don't forget to draw all your formal charges throughout your whole molecule. Don't neglect any of those. We have another resonance structure. These arrows are going to swing here. Bada bing, bada boom. Positive charge, negative charge, positive charge right here. Lone pairs, don't forget them. I forgot them. Cool. And now your last set of reactions is your any convenient base. Basically, coming in, you can use B minus. It's going to attack this hydrogen. These electrons are going to collapse back down, reforming the benzene, and this is going to be your final structure. Okay, yep. Cool, so this is going to be your final structure, and don't forget any convenient base. Right, so it is a lot of steps, but it is important to know how the nitration mechanism works. It is very, very common, as we saw in the previous questions. And yeah, on the final exam, expect mechanisms. I don't know which mechanisms will be on the exam, but this is a very, very, very important one. So I will definitely study this one up pretty well. Let's look at the next page. We have this kind of guided synthesis reaction, which should be fairly easy if you know your reactions. So let's start going to the left side. We have a chlorine being added to a benzene, and this is as simple as Cl2 plus FeCl3. And now we're given that. We have the nitration reaction, as we saw from the previous page. That is going to add a chlorine here and the NO2 down here. And now we're asking, okay, how do we go from the NO2 to an NH2? And this is your favorite reaction. This is your H2PD-on-C reduction reaction. All right, so now let's go on to the next pathway. We have this Friedel-Crafts reaction, and it is very tempting, very, very tempting to just add the chain kind of looking like this with our 3 carbons here. But do keep in mind that rearrangement can occur if a more stable product will be formed. So in this case, we have a primary carbon here, and this is going to be secondary. So doing the whole mechanism out, we're going to have a final product that looks like this. This was a spot a lot of students unfortunately got tripped up on, but it is very important that shifts can occur, and it is something that to keep in mind whenever we're doing any sort of reaction like this. So the next step is we have 2 empty boxes, which could lead to some confusion. But if we look at our last step, we have this oxidation reaction generating this carboxylic acid. And this is a very powerful reaction because it can occur to any benzene side chain so long as there's a hydrogen. And if we kind of look at what we have here, there is a hydrogen coming off of here. So we know that this can eventually turn into our carboxylic acid, and we just need to add this big tert-butyl group here. So in this case, we can just do Friedel-Crafts once more. Remember, we don't have any deactivating groups, so it is entirely possible. I don't know what I'm doing here. It is entirely possible to add your tert-butyl groups. So we need the chlorine, and then we need the AlCl3, and then this is going to be your reaction. The tert-butyl group here, and surely enough, this oxidation reaction is going to turn this into that, leaving the tert-butyl group untouched because there are no free hydrogens here. So now let's look at the very last question, question 21. Design a synthetic pathway to create the following molecule. And it tells us once again that Friedel-Crafts cannot occur with a meta-directing present. So it's very logical that we start with a Friedel-Crafts because we have an empty benzene. Friedel-Crafts is a very, very powerful reaction. So in this case, let's add this group here first. We have the Cl, and then we have this group here. 1, 2, 3, 4. 1, 2, 3, 4. We don't want to miscount any carbons or anything. AlCl3. Basically, this group is going to add right here, like this. And then we can go ahead and reduce this H2PD-on-C reaction. It's going to give us something like this. Cool, so now we can kind of go ahead and add the very next step as well. We can add this group here, and this is basically going to be another Friedel-Crafts reaction that we can do because we have an activator. We don't have any deactivators or anything on this molecule. All right, so we have something that looks like this, something that looks like this, right? And then the very last step is we're adding this sulfonyl group here, and this reagents are going to be SO3, H2SO4, and basically this is going to add in the spot that we need, which is going to be right here. So we have our benzene. We have this R group coming off here. We have this SO3H group coming off of here. Boom, we have this ketone type group coming off of here. So I know this was kind of a longer video, but it is very important to go through all the previous exams and kind of work through where you got any pitfalls, any mistakes. I finished this exam in around 30 minutes while explaining it. So if you guys really get down to practice, you can definitely knock out this final exam. It is definitely manageable. Do stay tuned because I'll be recording exam 2 and exam 3 reviews as well. What the exam is like 9 days away, so you guys still have plenty of time. Happy studying. Please feel free to reach out to me if you have any questions. Thank you guys.